This video is going to look at vectors in space. Just like we talked about vectors before, we were looking at only in the x and y axis, but now we're going to look at vectors in 3 space. So here, I'm not going to spend a whole lot of time. If you need to review vectors, you can go back and look at the videos for 2 space. But now we're going to have our 3 dimensions. So here we, once again, if you think of this, the x-axis here coming out of the screen, and then here we have our y-axis, and then going up and down would be the z-axis. And we had before our standard unit vectors where I was equal to the horizontal component before. Well, here I is going to be 1, 0, 0. So that's the unit vector here, I coming straight out of the screen, 1 unit. And then J is going to be the vector 0, 1, 0. That's going here on the screen left or right. So that's going here 1 unit to the right. And now, since we introduced the z-axis for 3 space, we now have k, which is 0, 0, 1. So that's the unit vector going straight up 1 unit. So here we now have the vectors I, j, and k, whereas before we were just looking at I and j in 2 space. So a lot of the things are going to be the same. It's just we're introducing the third dimension here for k as 0, 0, 1. So we're still going to have our vector u. If we think of the component form here, we're still going to label it as u sub 1, u sub 2, and u sub 3, where u1, u2, u3 is kind of thought of as your x, y, and z coordinates. So that's given us the terminal point of the vector where the initial point is at the origin. So it could be that we have the vector starts here at the origin and maybe the vector is going out here in this direction. Then the coordinates here for the terminal point would be whatever u1, u2, and u3 are equal to. So that would give us here the component form. And very similar, if we were looking at trying to calculate the magnitude, let me use a different color here. If we're looking at the magnitude of this particular vector u, and we use the kind of the double vertical bars here for magnitude, then just like before, it's the square root of u1 squared plus u2 squared, but now we look at the other component, which would be u sub 3 squared. And that would give us here the magnitude of u, which again, that is going to be here the length of the vector. Okay, so again, a lot of these are going to be the same formulas that we had in 2 space. So if we start out looking at an example here, let's say that we have the initial point for a given vector of -7, 3, and 5, and the terminal point is 0, 0, 2. Now keep in mind these are the points, and we want to find the component form. So how can we find the component form? And it's actually going to be the same thing that we did before in 2 space. So if you're looking for the component form, that means when we put it in component form here, that means we want to move the vector so that the initial point is at the origin, 0, 0, 0. So to do that, we're simply going to take the terminal point and subtract away the initial. So we're going to take 0 minus a -7, and then we would take 0 minus 3, and then 2 minus 5. And that's going to give us the component form. So here we'd have 0 minus a -7, which would be 7. 0 minus 3 would be a -3. And then again, 2 minus 5 is also a -3. So this here is the component form, 7, -3, -3. And we talked about the I, j, and k. So if we wanted to write this in terms of I, j, and k, we could think of this as 7i minus 3j minus 3k. So here, this is the same vector in terms of I, j, and k because I, j, and k are the unit vectors. All right, let's say that we have the given vector v is equal to 2i minus j plus 6k. Now, if we keep in mind, if it's easier for you to see, we can always write this here in this kind of component form. I would be 2i, so that would simply be 2 comma negative j is a negative 1, and then 6k, so that would be a positive 6. So that's kind of the same vector here. We could write it in the ijk format, or once again, 2, negative 1, and 6. And if we want to calculate the magnitude of this vector, we're simply going to take the square root of 2 squared plus negative 1 squared plus 6 squared. So then we get 4. 2 squared is 4, negative 1 squared is 1, plus 6 squared is 36. So we would end up with the square root of 41. So once again, that is very similar to what we did when we had vectors in 2 space. All right, the next topic we want to look at is the dot product. How do we multiply the two vectors together? Well, we talked about the dot product before, and once again, if we have our two vectors u, which in this case, let's say we have 3j minus 6k, and our other vector is v, we have 6i minus 4j minus 2k. And we actually want to find the dot product, so that's u dot v. And if you remember here, we're simply going to multiply the corresponding coordinates here. So here we have to be careful though. Notice the u, we have only 2 here. We have j and k. There is no I here. So what we have to realize is it's understood that we have a 0i. So when we multiply here, it's going to be 0i and 6i, 3j and negative 4j, 6k and negative 2k. Now, in this case, instead of using I, j, and k, you may find it a little bit easier if we were to kind of go to this component form here. And I'm going to rewrite this then as 0, comma 3, and negative 6. Whoops, not a parentheses, negative 6. So here we have our component form of u dot product with v. So then we would just simply write 6, negative 4, negative 2. And now when we go to multiply, we would simply take 0 times 6 plus 3 times negative 4 plus negative 6 times negative 2. And if we do that, we're going to end up with 0 minus 12 plus 12. And in this case, the 12s cancel, so this is actually equal to 0. And the key thing we want to notice here, as before with the dot product, notice the answer turns out to not be a vector, but it turns out to be a scalar. In other words, it turns out to be just a single number. It only has magnitude. It's not like a vector where a vector has magnitude and direction. So once again, the dot product, the answer is going to be a scalar. Okay, one last example here for this video. We have 7 times the vector negative 1, 3, 2 plus the vector 1, negative 2, negative 2 minus 1/5 times the vector 5, 0, negative 5. So we want to actually simplify this. And the first thing we're going to have to do here in simplifying this is we need to take care of the scalar multiple. So here the 7, once again, is multiplied by the first vector. So we need to distribute the 7. And we would end up with negative 7, 21, and 14. And then we would have 1, -2, -2. And here, once again, we have the 1/5. So we need to distribute the 1/5. And here, I'm actually going to distribute the negative sign with it. So when I multiply here, I'm going to multiply by a -1/5. So that means I can write this as addition here instead of subtraction. So a -1/5 and a +1/5 is a -1. And then if we multiply by 0, it's going to remain 0. And a -1/5 and a -5 would actually equal a +1. So now we have our three vectors, and all we have left is to add the three vectors together. So we can simply add them together. We would have -7, 1, -1. So 1 and -1 is going to cancel, so we're left with a -7. And then we would take 21, -2, and 0. So 21 minus 2 would be 19. And then 14, -2, and 1 is going to be equal to 13. So here we have the vector -7, 19, and 13. So keep in mind here, you'll notice a lot of the procedures we're doing here with vectors in 3 space, we've just simply introduced the z-axis. So now we have our vectors I, j, and k. The magnitude is calculated the same way. Same thing for finding component form. If you're given the initial and terminal point, keep in mind it's always the terminal point minus the initial point. And then if we have our vector, the magnitude, once again, you're just taking the square root of each of the components squared. Dot product is same as 2 space. You're simply multiplying the corresponding coordinates, and you're going to add those numbers together so that your answer turns out to be a scalar.